Welcome back to part 2 of our video on creating a custom RFNoC FPGA design. My name is Eckhard Ohlmer. I am one of the product architects for an ICE software-defined radio product line. We outlined the two variants of how to get from a set of FPGA IP blocks to a bit file and deploy it in our previous video RFNoC in 10 minutes. In this video, we focus on the text and command line based variant shown on the right hand side. In part 1 of this video, we focused on the image core YAML file that defines our FPGA design. In part 2, we'll cover how to instantiate additional FPGA IP blocks. We'll compile a bit file, deploy it, and validate that the additional FPGA IP block is part of the bit file. More specifically, we want to get from a standard shipping FPGA design for USRP X410 to a design where we add FFT and cyclic prefix processing statically into the data path. For that purpose, we are going to create a copy of the standard image core YAML file, and then we show how to modify each section in there. So in order to create a custom image core YAML, we'll first need to clone the UHD repository. Once this is done, we navigate to the FPGA top folder where the image core YAML file we want to modify is located. Then we create a copy of the standard image core YAML file and we're gonna give it a new name. Now we open that new image core YAML file and modify it as shown on the next slides. So note that we will also share the modified image core YAML file we prepared in this video. In the first step, we need to free up some FPGA resources in order to fit multiple FFT blocks. So let's do that by removing the replay block, as we do not need it for the application we have in mind. For this purpose, we have to remove the lines in all sections, as shown in this slide. In the second step, we add the FFT blocks within the doc block section. Note that the same block can be configured at runtime to act as an FFT or as an IFFT. First, let's instantiate a 2-channel FFT block with cyclic prefix insertion capabilities for the first 2 transmit channels. Then let's add any compile time parameters that we want to change from the default values. And those default values, they can be found in the block description file. Also, the parameters themselves, they are explained in the block's top-level HDL file. Next, we instantiate a 2-channel IFFT block for the first 2 receive channels. And note the difference in cyclic prefix handling in there. And finally, we repeat these steps by adding another FFT and IFFT block to cover the 2 remaining transmit and receive channels. In the first step, we modify the static connections to connect the in and outputs of the FFT block. Let's go through the connections for the first radio channel in more detail. In the transmit direction, stream endpoint 0 connects to the IFFT input 0. The IFFT output 0 connects to the DOC input 0, and the DOC output 0 connects to the radio input 0. We need to do the same for the receive direction. And finally, we repeat these steps for the remaining 3 radio channels. In the last step, we need to check whether the FFT block requires any extra clock connections. In the block description file shown in the bottom right, we see that it requires the 2 standard clocks that are automatically connected to the block and the compute engine clock. So let's add the compute engine clock to all 4 FFT instances. So we add the connection to the first FFT block and then the connection to the first IFFT block. And then we repeat these steps for the second FFT and IFFT blocks. Now that we have completed our image core design, we can compile the corresponding bit file. We start the folder where the modified image core YAML is located. Next, let's check how the image builder command line command should be constructed by typing RFNoC image builder minus help. The help illustrates how the command can be composed and what the different options mean. As we are already in the folder where you modified our image core YAML, we can simply type -y for using the YAML file as an input and add the YAML file name after that. Let's start to compile. You can see a number of warnings and some of them are marked critical. This is expected during FPGA synthesis, especially since we develop reusable code for multiple product variants. In Vivado, the classification of warnings, particularly what is considered critical can change between tool versions. So in the meantime, the compiler is completed. Let's inspect the results. We are still in the folder where the image core YAML is located. At completion of the compile, we can find 3 new folders. The build folder contains the final compile results. In the build folder, we find 3 files. .bit file, this is the actual bit file that will be flashed to the USRP FPGA. .dts file, and this is shown in the middle of the screen, and this is the so-called device tree overlay. It specifies the FPGA device interface to the embedded operating system running on the USRP's ARM core. And finally, a .rpt file shown on the right. This file lists the FPGA resource utilization. In the next step, we'd like to deploy the FPGA image to the FPGA using the image loader tool. We'll need the bit file and the DTS file to be present for this operation. From within the build folder that contains these files, we run UHD image loader. We need to specify the device type, the device IP address, and the correct bit file name. Once the flashing operation completed, we can run the UHD USRP probe tool. This tool lists, amongst other things, the NOC blocks that are present in the device, as well as their static connections. If you run UHD USRP probe, you may see warnings related to host site buffer sizes for streaming. So for the purpose of this video, we adapted these buffers as discussed in the Ethos knowledge base so that there are no warnings. We can use the output of UHD USRP probe to validate that the FFT blocks and the respective static connections are actually present in the FPGA image. First, let's compare the FFT blocks we defined in the image core YAML file with the NOC blocks found in the image. The output of UHD USRP probe confirms the presence of the 4 FFT blocks that we instantiated. Next, let's see that all NOC blocks are properly statically connected. The static connections defined for the first transmit channel in the image core YAML match the output of UHD USRP probe. And the same match can be confirmed for the other transmit and receive channels. In summary, we can confirm that the correct number of FFT blocks is present in the FPGA image and that each FFT block is connected as defined in the image core YAML design. Congratulations! We have mastered the workflow that gets us from a set of FPGA IP blocks to a custom FPGA image. In part 1 of this video, we learned how an FPGA image is defined in the corresponding image core YAML file. In part 2 of this video, we have modified the image core YAML file of a standard FPGA image by adding OFDM functionality. So now we are ready to develop an RFNoC application using that bit file. Stay tuned.